Hello everyone, I'm Qiao Zhang. I'm a first-year PhD student at Drexel University. Today I'm presenting my research on going online, a simulated student approach for evaluating knowledge tracing in the context of mastery learning. This is work done in collaboration with my advisor, Christopher McLennan. Intelligent tutoring systems ITS can provide inner loop feedback about steps within text and outer loop feedback about performance on multiple tasks. Our work mainly focuses on the outer loop approaches. Knowledge tracing algorithms are embedded in the tutors to keep track of what students know and do not know. The models take labels of the skills needed to perform each step, also called knowledge components, KCs, as students first attempt correctness to predict whether the students will correctly solve a new problem containing that KC. Many studies have proved the efficacy of such approaches in offline settings, but little work was done exploring their application in online settings. We fill this gap by running online simulated experiments to investigate a few knowledge tracing approaches. So, what is knowledge tracing and why is it so important in designing IITS? By definition, it is the task modeling students' knowledge over time so that we can accurately predict how students will perform on future interactions. There are multiple knowledge tracing approaches, like Bayesian knowledge tracing (BKT) by Corbett and Anderson in 1994, three-in-a-row or the Streck model by Heffernan and Heffernan in 2014, and deep knowledge tracing by Peach and others in 2015. Both the BKT and the DKT model have a few model parameters. For example, the BKT model has four parameters, denoted as pknow, plearn, pguess, and psleep. This graph demonstrates how BKT model student knowledge in a hidden Markov model as a latent variable, and the state is updated by observing the correctness of each student's interaction in which they apply the skill in question. Then, where do the initial model parameters come from? Would they affect the model performance? And how can we obtain them? With those preliminary thoughts, we intend to answer two research questions. Firstly, can we run simulated experiments to get some data and generate the model parameters when we do not have human student data? Secondly, talking exactly about online knowledge tracing, what would be the best or probably most appropriate knowledge tracing approach? From our observation in literatures, we noticed that the model parameters were manually picked in some of the studies. In other studies, the researchers ran a pilot study to first gather some data and tune the model parameters. But this process requires extra time and labor. A/B testing seems to be a reasonable approach in evaluating models with different parameters. But similarly, it requires a classroom study and IRB approval and also lots of efforts. Therefore, it might not be feasible to conduct multiple experiments, evaluate each model, and identify the most outperformed one. In our approach, we ran simulated experiments with the evidence learner architecture, which is a framework for modeling human learning from demonstrations and feedback in digital environment. This framework supports a few different tutors with the goal of teaching different skills. The evidence learner agents are simulated students generated by the AR framework. They utilize artificial intelligence and machine learning mechanisms to simulate human learning. Next, I'm going to show the training process. Here's the HTML interface that the simulated student interact with. We are using the fractions arithmetic tutor for this study, which consists of three types of problems. Adding fractions with different denominators, AD, adding fractions with the same denominators, AS, and multiplying two fractions, M. To explore different knowledge tracing approaches through simulation study, we implemented 6 knowledge tracing conditions. Random as a baseline model, the Streck, also string-a-row model, BKT model with default parameters, with human-based parameters, and with simulated parameters, and lastly, DKT model with simulated parameters. The only difference of each condition is how the next problem is selected for the simulated students. We created 30 simulated students for each of the 6 conditions, providing 80 questions for each of the 3 question types and analyze the data generated. There are a total of 14 knowledge components in our analysis, 8 for AD, 3 for AS, and 3 for M. Each KC for each problem constitutes a unique skill. To answer our first question, can we generate model parameters through simulation experiments when there's no human student data available? We did a correlation analysis of the random-based BKT parameters and human-based BKT parameters. This figure shows a positive correlation of around 0.65 in the learn parameter, which means the simulated students generated by average learner have a similar learning rate as the human students, indicating that our approach of obtaining model parameters is pretty feasible. Then we took a closer look at the numbers of problems administered in each condition. The random tutor always takes all the problems for each type. The strict tutor takes less problems than the random but more problems than the BKT tutors. The 3 BKT tutors take similar numbers of questions in each type, and the DKT tutor almost take all the questions in A different but only less than 3 questions in AS and M. To get a better sense of the overall differences between the random, strict, BKT random, and DKT conditions, we then use the addictive factors model AFM to examine the learning curves. Here we plotted the overall learning curves for the data from these tutors. This figure shows that the BKT tutor stops giving practice earlier than the strict tutor, which subsequently stops giving practice earlier than the random tutor and the DKT tutor. To better compare across models, we introduced an efficiency score by having the predicted correctness at the end of training divided by the number of opportunities and students received for each student and each KC. We then average over students to get an efficiency score for each KC. Finally, we average over KCs within each problem type. This table demonstrates 3 model efficiency scores for each of the 6 models. The bigger the value, the more efficient the model is. The model efficiency score complements accuracy and provides more information for use in selecting the best knowledge tracing approach. Then we want to look at the probability that students will get each skill correct at the point where the model assumes they have reached mastery. This figure shows the average predicted correctness after the final practice opportunity for each skill. For most cases, the prediction is higher than 95%. Which in turn suggests that the students have obtained mastery in these cases. Unfortunately, the KC AD answer denominator, which refers to computing the answer denominator in at different problems, has the lowest overall next step practice prediction in all 6 conditions. Diving deeper into this KC, we perform sequence analysis to visualize the predictions at each step by different knowledge tracing approaches. This figure shows a comparison of the predicted correctness at each problem-solving step among the BKT model with random-based parameters, the strict model, and the DKT model on the AD answer denominator KC for a single student. Both the BKT model and the strict model provide consistent prediction over time, while the DKT model predictions tend to jump around, but generally do not seem to be increasing despite getting the problem correct multiple times in a row. Upon further investigation, we found that the DKT model tends to use predictions to decide which cases are mastered so it can pick another problem. Unfortunately, for multi-step problems, some cases cannot be correctly answered on the first step for next problem because there's an order of using the skills to solve the problem. This results in a side effect of confusing the mastery learning system into thinking that the KC is unmastered. Because previous work by Pitch and others only looked at problems that had a single step, so this issue never occurred. To summarize, our results prove that simulated students can successfully test online knowledge tracing approaches. The strict model works well for mastery learning and has reasonable efficiency, though it seems that this model is giving a bit more practice than strictly necessary. The BKT models also work well for mastery learning and generally seems to have the best efficiency of the approaches we compared. Multiple studies suggest that the DKT model has good predictive performance for offline predictions, but we found that it does not seem to work properly for online knowledge tracing, particularly in cases where problems have multi-steps. We also have a number of additional future directions we would like to explore. This is all for this presentation. Please feel free to reach out to us if you have questions or thoughts. Thank you so much for your time.